Parallel plate capacitors are used all over electronics, and they're very common. It's a way to store charge. When there's not an electric current running, you can store it inside a parallel plate capacitor. We also have parallel plate capacitors in defibrillators. This is, if you think of the two plates of the capacitor, this is one of the plates and this is the other, and they get a very large voltage or potential difference, and then that is transferred through the human body to help restart a heart. So when we charge a capacitor, this is a circuit. We have a battery with the positive end and the negative end. Charge starts at this end, leaving a negative charge on this parallel plate, and it will travel through the battery and to the next plate, ending up with a positive charge on this plate. So over time, there'll be a potential difference between these two plates as the charge builds up on each plate. As soon as the potential difference between the two plates matches the potential difference of the battery, the capacitor will stop charging. It would also stop charging if you disconnected the circuit, but it's going to reach a maximum that's equal to the potential difference of the battery. And if we remove the battery, the capacitor remains charged, and the potential difference will still be equal to the battery voltage. So it's a way to store charge even when there's no connected circuit. So capacitance is a property of a capacitor, and it's actually any object's ability to store electrical charge is its capacitance. In a capacitor, we have parallel plates. They have an area, and then there's a distance between them. That area and distance will define the capacitance, and we use the K constant, which I'll talk in a second, epsilon naught, times the area divided by the distance. That is the capacitance. We measure capacitance in farads, although oftentimes it'll be microfarads or picofarads. K is going to be just a constant called the relative static permittivity. Sometimes we call it the dielectric constant. For most problems, unless we say otherwise, K is just equal to 1. For vacuum, it's 1. For air, it's very close to 1. But if we put a dielectric in between the capacitor, we'll talk about that in a few slides, then we do change the value of K. And epsilon naught is the permittivity constant, which is given on your equation sheet. A is the area of the plates, and B is the distance between the plates. So a dielectric is when you put a material between the two plates in a capacitor, and that will increase the capacitance. It's increased by a factor of the dielectric constant, and that's the K. So for air or vacuum, for vacuum it's exactly 1. For air, it's close enough that we treat it as 1. And if we add other materials like Teflon, paper, Pyrex, anything else, we're going to increase the capacitance by these factors. These are the equations that are on your AP Physics 2 equation sheet. The potential difference of a capacitor is going to be delta V equals the charge over the capacitance. We also know that the energy of a capacitor can be defined as 1/2 Q delta V. And 1/2 Q delta V, if I replace the Q with delta V times C, we can also write it as 1/2 C delta V squared. These equations are on your equation sheet. The electric field inside a capacitor, we've done this already, is Q over epsilon naught over epsilon naught times area, and the capacitance is defined as K epsilon naught A over D. So let's do a problem. Let's say we want to charge a capacitor. We have a capacitance of 1.3 microfarads. It's connected to a 1.5 volt battery. What is the charge? So once it's charged, the potential difference on the capacitor will equal the potential difference on the battery. We can use the equation given and solve for charge. Charge equals capacitance times the change in potential. We plug in our numbers, make sure you do 10 to the negative 6 for a microfarad, and we get 2 times 10 to the negative 6 coulombs. Here's another question. How much energy is stored in a 220 microfarad camera flash adapter that has been charged to 330 volts? So we're solving for energy. We have the capacitance and the potential difference. Now, the flash of a camera is a capacitor. It's able to store charge. We charge it up, and then we use it when we do the flash. Use the charge when we do the flash. So we're going to use our energy equation. Since we know capacitance and potential difference, we can just plug in our values, making sure to use 10 to the negative 6th, and we get energy of 12 volts.